Hello, gentle readers, curious earthlings. Welcome to another installment of Logos 2000. One of these couple hundred hours of lecture talks in a brief sort of setting where my interest in study has been foundations. Wanting to know what a theory could be. Foundations is the idea of the ground, the alaya being the term kind of from Buddhism for a foundation, a ground. The ground, or grund, is another word for the grounds. The foundations is the idea that there is perforce a theory of that's reasonable and rational, at least to some abstract reasoner, rational thinker, that has within it all what is so entailed, what's in a modality that there exists one, in a kind of univocity, that there's a universe of things, that everything exists in it, and that it has things that match our science and our reasoning and our information gathering and our great experiment about science, which matches because one of the great and profound successes of science has been that it always finds that the same sorts of laws hold true everywhere, and it's possible to get good theories, that good theories are not wrong, is the idea. And that there's a notion of right and wrong, or correct and not correct, which isn't always so the case in issues in the human condition, which is a rich milieu, and it's part of philosophy, and it's part of life and the living of life, the human condition. That foundations yet is still what is a good theory, and why is it so? So in mathematics, they have various ideas how to approach this. And you can kind of turn to the beginning of the 20th century, and there's a fellow named David Hilbert, and he said, is there ever going to be a mathematics of all of mathematics? Can there be a theory of all of mathematics? If so, how can that be so? And then as part of trying to figure this out, then he's also famous for all these problems, which were conjectures of the time. And then over time, a few of these have been variously shown or not shown to hold or shown to not hold. The conjectures, according to Hilbert's problems, that the idea, though, is that this greater course is called Hilbert's program. And then here, sometimes when he talk about infinity, Hilbert would talk about like an infinite hotel to illustrate an occupants of values in the space of all the integers, the infinitely many numbers. So there's Hilbert's problems, Hilbert's program, and Hilbert's hotel, and which is infinite. And so then that itself already gets into some ideas whether or not it's always the same place. Because one way to look at infinity is that there's none. It's just there are infinitely many, but no infinitely grand numbers. So in this kind of usual, and in the usual course, numbers just means an integer continuum. So the integer numbers, the whole numbers, the counting numbers, usually starting at 0. Although in some definitions, it starts at 1. So either way, just starting with these being non-negative integers, and infinitely many of them as with regards to whether they're infinitely grand. Then the idea that there's a standard model of this infinitude of integers is kind of as regards to whether there exists an inductive set that's complete. And so that as an inductive set that's complete, when earlier it was considered that, well, a number is just kind of a set, an object with only one type of relation, one kind of relation, then all the different relations that it has with any other sets are just due to membership being an element of one of these sets, or in a given number of them in the structure that it is. That this inductive set of the infinitely many elements would contain an infinitely grand element. And so this is oftentimes called, for example, Russell's paradox. For Bertrand Russell, And so he was a logician, and for the first half of the 20th century, very, very famous. And what was in it is that he said, oh, well, if you have a set of all sets that don't contain themselves, like if these are the only ones, these finite entities, whole numbers, it would contain itself, and thusly it would be not so that the statement that it only contains infinitely many and not the infinitely grand numbers, that the infinity of numbers thus automatically makes itself so that if there's a fragment of it that makes a model of an inductive set, integers, that there's as well then automatically one that contains itself, and so it has as a member an infinite member. So what this means is that then the other idea is that there are fragments. And so usually when we frame things in terms of the bounded and unbounded, meaning it's like if it's bounded, if its upper bound is 10 or 100 or 1,000, it's got an upper bound. And it's unbounded if it does not. So then the idea is that, well, can there be a standard model of only all the infinitely many finite integers? And so in some sense, Russell's paradox makes it so that it can be, and then the answer is no. And so, and then when this is so, then there's still fragments, each of the finitely many finite numbers beneath a given bound, fragments, and extensions. This is after Skolem and Lowenheim, who were set theorists and logicians in this time when, after modern mathematics, it came to be that the enterprise known as axiomatic set theory, Zermelo-Fraenkel set theory, and make for descriptive set theory, was to be the candidate for mathematical foundations. That already Skolem demonstrated that there are extensions and collapses of the models of these infinite collections for each other. And so that there's one, and it's not just the one where it's like a bigger collection is able to fully model a smaller collection. There's also one where a smaller collection in cardinality is able to model a bigger collection. And so this is pretty astounding, and especially after people have basically said that after Russell's paradox, with which it was used to kind of say that Frege's Grundgesetze and ground rules, ground laws for reasoning, including the infinite and infinitely many, was failed because Russell simply pointed out that this is a paradox, or a contradiction could be arrived, so the whole thing is over, kaput. Now, what happens then when it's just kind of said in an axiom that that's so? It's a sort of restriction of comprehension. You might otherwise assume that always you'd have an expansion of comprehension. And like a scientist, has to have, it cannot merely ignore a piece of data for any reason at all. I mean, it has to be carefully, made as for its own explanation, and as to why and whether or not it's part of the design of experiment and the implementation of experiment, according to the energy of experiment, the conditions and this kind of thing, that the data otherwise would always assert itself as being so. Now, in mathematics, this is not quite the same thing, because via naive comprehension, then this gets into a whole thing about set theory. When you're starting to study set theory, in getting into the transfinite, the infinite and beyond, is that there's inconsistent multiplicities or not. So the idea after Russell and Zermelo-Fraenkel set theory it was like there is an infinite set and it's an inductive set and it has no infinite members and that's it. But when the only thing already yet in this theory is the set of sets that don't contain themselves, which would, Russell's retro thesis then kind of is evoked, to define that there is a standard model of integers, that there is a particular integers that has all the infinitely many finite members and no infinitely grand members. Well, that's kind of so and not so, because otherwise what we're looking at is that there's always only fragments of models of integers, or there's extensions of models of integers. So a model of all of the integers is either at least missing some, or it's got more than where it would be specified by a naive inductive set. So they call it naive set theory to say that instead of that, we're going to have this restriction of comprehension, and so then in some direct things we can just arrive at that being no longer a thought. But instead, that's kind of like the naive set theory is that restriction of comprehension, because it's trying to erase a mathematical fact. It's just what it is. So it's not a bad thing to have the idea that infinite models of integers are either fragments or extensions. That's just as perfectly suitable. And then to say that there's one that's neither of those and somehow fits the middle, when by its very consideration infinity is infinity plus one, or this kind of thing, that's still what it is. So that the very vagaries that get introduced when infinity is, as of among the numbers, infinity is equal to itself plus one, when no other number is like that, because all the other numbers are finitely grand, and then the ones that are infinitely grand have anything different at all, make for that so why infinity is thusly a really relevant thing in foundations. And would it really matter then? What does it really matter? Why would one want to have the consideration where it's just not given as a fait accompli that infinite induction has a base case for its existence, as it were, this inductive set that doesn't necessarily otherwise admit that it's only either a fragment or an extension? It's non-standard, say. So why would that be useful? And then the idea is that it's useful because that gets into, then there's more than one law of large numbers. That it's possible to arrive at, there's places where, like in the infinite bounds, that basically things go over or things go under, or the usual course is the same as the law of small numbers, that it takes infinitely many, but none is infinitely grand. So it's the unbounded case is in the middle and right down the middle. But there's these two other cases that are part of the structure, and they're always there. They can't just be defined away. It's not like just let so and so be so, because via this expansion of comprehension and the matters of the objects themselves, it's arrived at. There are these other laws of large numbers. So the fields where that shows up a lot are ones where otherwise the estimates and predictions, the guesses made by mathematical models, fail. Probability theory usually comes to mind, and that because it's probability theory is much of the most sort of practically applied for statistical inference. All such matters of models, from like models for insurance, or the estimated balance to result to offer a cost competitive insurance plan, or for matters of for many matters of expectations and conditionals, then that the conditionals and expectations derive to define not only what would be conditioner related, yet also contingent. That what would be, if it is so, then to be like so, or if it is like not so, then to be like so. These ways that probability theory and statistics then has seen much of the use of these laws of large numbers. So some of the things we've read about that here with regards to there being more than one law of large numbers, for the unbounded case and the infinite cases, that the supermartingale is one that is sometimes arrived at. But then also as with regards to random motion, random walks, and the Wiener series, or Markov chains. Wiener chains or Markov chains, which are kind of flipping coins ad infinitum, whether at the end it's spinning or heads or tails. So the supermartingale, it falls kind of under the ideas of these supertasks. A supertask is something that happens kind of like in Zeno's thought experiment, half and half and half and half again until ad infinitum it equals the sum of those put back together. Then these other models, like it doubles that or it halves that, being basically the idea is like, well, if there's going to be three laws of large numbers, we'll just say one's double and one's half. And then that it actually kind of works perfectly well then when we have Cantor space and we got Borel with almost none and combinatorics with almost all, and then we kind of have our square Cantor space with half right down the middle, both ways. That this is part of the laws of large numbers, and why it is so that in the infinitary reasoning, then it's possible, after kind of considering how a structure like that would be, then some symmetry concerns, that it adds up to make for these cases where Borel, from the story as a Borel spaces, and how many of these sequences would be absolutely star distributed or equi-distributed in every given base or radix, the zeros and ones, all of them, each one different, has for that Borel and combinatorics arrive at one says almost all and one says almost none. And then there's one just from this line drawing iota values that comes right down the middle and happens to be equal to exactly 1/2. So we already have at least three notions of infinite models of integers: a standard, infinitely many yet no infinitely grand, of fragments with almost all of the infinitely many and no infinitely grand, a fragment, or an extension, infinitely many and at least one infinitely grand, maybe infinitely many more, infinitely many more, infinitely many more. So we got 3 laws of large numbers, 3 continuous domains: the iota values, the line reals, the complete ordered field, the field reals, signal reconstruction, the signal reals. After an integer continuum and a long line continuum, these linear continuums, real numbers, real valued numbers. 3 different kinds of perspectives on what Cantor space, the space of all the sequences of zeros and ones that are each themselves infinite, with a beginning at no end, whether they're fragments or extensions or standard, is a piece, the more of these possibilities. That then the reasons that get into why this makes for like 3 kinds of natural infinities in these natural numbers is because it exists like this, and it's easy as to just write down in a few pages these formalisms to make it so that it stands upright like this. So why then the infinite has always been at issue and at odds, and otherwise the consideration is, first of all, that there's arrived at inconsistent multiplicities, because what are the inductive grounds to pick one of these? Well, it requires a deductive account and inference. Well, is that as simple and easy to relay? It's like most people have that as possible. Yeah, at the same time, it has to be book kept then, and there has to be the kind of this greater outside structure arrived at to be able to say why there's any meaningful differences between these at least 3 kinds of natural infinities apiece. Then mathematics to keep things tractable for forever. Since the Pythagoreans, is like everything is, furthermore, it's rational, and it can be infinitely precise almost, but it would be just infinitely grand almost, the 2 integers ratios that express any given number between 0 and 1. And there's an idea in this sense that the rationals are huge, and so this signal continuity has that, well, if it's a fragment, it's rational, and if it's an extension, then it's real valued. It fills those. That's these signal reals in a sense. Whereas the complete ordered field is yet again, it's countable and it's rational and it's perfectly rational. Each one of its members, all of them, because it's standard. It's based upon a standard model in this sense. That when and where it's possible to say that there is no standard model of integers, or that a standard model of integers is somehow both of a fragment and extension, or that there's only a standard model of integers, which is most people's usual takeaway from being told that rule number 1 is that there's an inductive set, it's infinite, and it's has no infinitely grand members, it's infinitely many. That's just kind of the way it is. And then a lot of mathematics has been built on that, kind of leaning all that one way. Leaning all that one way, saying there's a standard infinity, and now everything else is just so follow from the complete order field. Delta epsilon x, all of analysis exists from this. Yet non-standard probability theory is a thriving field of application, which doesn't always have this in place. Other things that get into this that are based on laws of large numbers and probability theory include the central limit theorem and other limit theorems. And as well, they're major deals in convergence, that series converge and have a limit, and so in the infinite, the series achieves exactly this value, this limit. And some series converge quickly or fast. Some converge slow. Some appear to converge quickly and fail to converge, and some appear to not converge and slowly, yet do converge. So this helps to reflect upon that there's simple criteria as after the law of small numbers, our standard law of large numbers, and these other ones, which may be about properties of the real numbers and properties of the integers, these natural infinities, which almost always then tend to be like some kind of scalar infinity, because then you want to measure something by doing the analysis over this region of analysis and arriving at measure, and it's kind of called the measure problem. How do you measure something, and this kind of thing. With regards to the sigma algebras, the sigma for sum, to sum these things together, they're algebras, and then each one of those having a well-defined and not necessarily finite, it may be a vanishing region that yet all together add back up. That then these other ones with the doubling spaces and halving spaces reflect very well that Vitali's construction and Vitali and Hausdorff's constructions of a doubling space and doubling measure from dividing a unit line segment into bits and then trying to fit it back together. It's kind of like opening up a suitcase and then unfolding things and trying to put it back together. It takes twice as much. Or Banach-Kantarsky, who it's named for usually these days now, would have kind of an algebraic approach. But Vitali and Hausdorff have this geometric approach, how two balls of the same size result from taking one ball into pieces, on only a few pieces, and that those two of those pieces and two of those other pieces fit back together again, and each one form the same size, the same measure. So equi-decomposability is this idea that doubling measures and halving measures, or doubling spaces and halving spaces, are real in the real linear continuum and the real values and the real valued. And there are long-standing results about how to revitalize, to make for vitality again, kind of after this course, revitalize measure theory, because then these days it's arrived at, it's like, well, what do we have in measure theory? Well, we got a measure problem. What does a measure problem mean? Well, a measure problem means we don't know, and so we've lost the ability to add back up these things that come out of it. And the first example in that in physics would be like, well, we add these all up, we get infinity. And so we need to get something finite, but we just end up looking at averages because we're looking at something that happens super classically. And so when we try to add it up, we get something infinite. So but at the end of the day, when we measure it with like a candela meter or something like that, how many candles is that? And it's a finite number. It's one, say. It's a natural unit of things. So these natural infinities kind of do relate to the natural unit of things. And it does reflect on the fact that usually when we're talking about the natural numbers, that's the integers. Are the counting numbers, the whole numbers, the non-negative integers or the positive integers. These are usually considered the natural numbers. And then with regards to there being a standard model is, of course, given in most usual accounts like Zermelo-Fraenkel set theory. And it's great success. And it's contrasted then with naive comprehension, because some of the axioms of Zermelo-Fraenkel set theory are restrictions of comprehension, that these things otherwise would not exist. Whereas, and at the same time, there are only two constants introduced in Zermelo-Fraenkel set theory. empty, the zero, the empty set, and this infinity. That the axiom of infinity is itself both an expansion of comprehension because it's given as a definition that an infinite inductive set exists, and a restriction of comprehension because it says it's not an extension and it's not a fragment. Whereas otherwise it's arrived at that, according to Skolem and Lowenheim, it is both of those with the same structure and intent in set theory. And it is well given that for what it is when it's only the numbers and that those are only the sets, that it's Russell's retro thesis is what I call it. That it's not so. That its definition is without having made other naive comprehension wrong. So there's a wrong involved, and then we want to look to try and figure out, it's like, well, there must be some unwrong about it, because these are the numbers. Eventually, to arrive at that, there's no reason not to think that all the things in nature just do add up, and that emergence, the property of emergence, is usually enough it's convergence, because it's like, well, what emerged is exactly what's standardly predicted according to the way these things are. It's a natural, say. But then these other ones, emergence in the case when it's like, well, this added up 2/3 as many butterflies, or we're not quite sure, but this teacup and this hurricane don't line up. Emergence, then that gets into how these things like the supermartingale and the supertasks. Where the supermartingale is that the martingale is this idea that a gambler doubles or nothing until they walk away a winner. And the idea is, well, there's either a limit or a bust, and so they either don't have enough stake to take it to the next round, or that the other player has a limit and they can't make a stake for the next round. So they can theoretically lose until they finally do double their money on some kind of fair coin toss or Bernoulli trial game. And with regards to why the martingale is in any kind of finite scenario, of course, is a loser. Whereas with regards to that in the infinite limit, it goes other way, and it would be something that nature has as its own processes, which basically model that as being so. So those are the super tasks then. A task that is not just for infinitely many, according, for example, by division by time, infinitely many steps in the task. All the infinitely many of them, which is an infinitely grand number of them. So what you'll find is most standard accounts, of course, say nothing at all, except there is the standard and only the standard. And that then one thinker that I point to a lot is Mirimanoff, because it says there's the extraordinary. So the ordinary means also standard. And so we say well-founded, ordinary, or regular, because it's regularity in the sense of well-foundedness, to line up with this other axiom of Zermelo-Fraenkel set theory, that there are no infinite descending epsilon or Elt chains, regularity, well-foundedness. So that's kind of like half of the axiom of infinity in ZF, which is like, there is this constant, it is an inductive set, and it's not irregular. Even though, yes, you could read that right off from how it's built, these numbers, and the most usual simple model of numbers that everybody else uses for all their ordinals ever since then and after that, why it would be a contradiction and inconsistent multiplicity. So that goes to show that it's not free of this controversy, say. Well, at the same time, figuring out anything else would be called anti-foundational in a sense, like for Boffa, Finsler and Boffa and Axel, and maybe Dana Scott. After the set theory, of course, some people studied it and said, well, what about sets that are not well-founded? What about sets that are infinite and eventually contain themselves again, say, that the relation goes around? So it's like, it's an entirely different structure. It's much simpler to have a theory of only one relations if nothing ever relates to itself. It's like, well, where does equality come in from them? And it's like, well, it's kind of complicated, and please don't ask. But it's kind of the opposite of something that doesn't contain itself, something that does contain itself. In a theory with pure equality, That would be the relation, see? But yeah, we still have equivalence classes and all these kinds of things that live in the logic that is used to build this up. Reading Quine's set theory helped a lot to pick up the case after Russell and Whitehead from Principia Mathematica and then Zermelo-Fraenkel set theory to help see and show that what goes into is like equality is kind of after the fact, and it's just about x and then the Russell's retro thesis is quite after the fact, and it's x not ex. That these two things end up by elt x not elt x. That these are two things that get into kind of why that they fit back together in the theory and make for an extraordinary theory and not quite well founded yet having well founded fragments or extensions of the well founded, or having the infinite, and then figuring it also that among those is any descending L chain of ordinals, that the ordinals are another way to say the counting numbers. And so the ordinals are like the serial order of things, whereas the cardinals are the count of things, and counts relate to any of the other counts. So cardinal numbers are giant equivalency class of counts, and as was discussed here, it's like 1 is the loneliest number, or maybe it's infinity over 2, or infinity choose infinity over 2. The largest equivalence class of cardinals, the cardinal that most things in the universe have as their cardinal, that often enough it's just considered to be 1. So it's cardinals. And then ordinals is just like ordinals is like 0 is contained by 1, is contained by 2, is contained by 3, and they are ordinal. And they don't really have anything else to do with like number theory, because this is before the number theory's numbers even have the rest of their character. For example, addition or multiplication or powers, is that iterated again? Here there's a great account after arithmetic that there's an increment on the one side, and that's usually enough called successor, like the successor to a given ordinal is the next one. And that's where it's usually defined, whereas the count is usually defined as that, well, all the things with count 2 have 2 things with count 1, and all the things with count 3 have 1 thing with count 2, or all the additive partitions that building up what builds these things is, opposite for cardinals and ordinals. That the extraordinary theory makes for ordinals, and then when that's to be the inductive set, because that's the cases for induction are just ordinal, next, and this kind of thing. That's like how it is so, that ordinals and cardinals are different. And in set theory, modeling ordinals is not like in ordering theory, modeling sets. Because there's another theory of one relation, it's called ordering theory. And it can be just entirely different. All the models, even though it only has one relation to deal with and carry out. And these other things that then just get equipped for it, or is so simple and naive. This here is the heno-theory. It's like one universe of mathematical objects that somehow has a way to look at it when the theory, it's also all the fundamental theories only by themselves. This is the one theory, all the theories, many theories, all one theory. So we have ordinals and cardinals, and then this extraordinary is from Mirimanoff. He noticed this and made it so. So Zermelo-Fraenkel's set theory at that point in time was just like, we're adding this, and then we're also going to add the axiom of choice, which means there exists a way to pick from each set like a first or least element. This is the well-ordering principle. So you got well-foundedness and well-ordering, that somehow there's an ordinal that applies these things, and then as well like a set makes for a count of these things that's somehow has a single cardinal. So that is a sort of brief introduction to the issues that get into why that when we're talking about infinity and laws of large numbers, there's more than one. And what inspired me to get started off this whole thing was Derrida and Husserl and talking about infinitary reasoning and the telos, of the reactivation of the infinite for geometry. And Hilbert, he at some point in time, he had a postulate of continuity. He came along, he's like, I've been studying mathematics, and it looks like to write it out and to write it all out as far as getting where I want it to be from my point set topology, which is how things are looking, they have to have an axiom or a postulate of continuity. Axioms, postulates, principles, any kind of introduced concepts or introduced constants have these as their terms. Why it is so that the very sorts of usual axiomatics has this baggage that goes along with it. The idea is that it's the least amount, that axioms are independent, they don't contradict each other, and not from them is it possible to derive any sort of inconsistency, except insofar as it would introduce at least two different things. So it can introduce diversity and variety automatically, is what it does. That's what expansion and comprehension does, building more objects. And then as with regards to the restriction of comprehension, and that's sort of considered non-logical. Here it's sort of considered a compromise in ZF set theory after Russell's retro thesis to say that there's a standard inductive set at all, when there's not, in a naive comprehension of a lesser theory. And it's not necessarily so when that just makes an opening for these different aspects of infinite collections. Why it's so that it's not the only game in town, say. Yet it is very successful, and it is quite well put together, and it does make a lot of the grounds for analysis, and most people have studied it as part of their mathematics background, and it's called, in a sense, modern mathematics, to say it is like so, compared to like Euclid's axioms and elements, real analysis, and trigonometry, of course, algebra and all this. Each of these are these different parts that go together, where the idea is that this descriptive set theory is then to be descriptive geometry, descriptive arithmetic, descriptive algebra, descriptive function theory, descriptive topology, and descriptive operator calculus. So, the analysis all together with all these different models. So basically just makes a reading of those as what would be it, instead of trying to find a way that's like, here's all the possible ways that there can be set theory at all, so they all exist, and then all these other theories kind of somehow naturally fit with that, with this idea of the axiomless geometry, after the axiomless natural deduction, all expansion of comprehension that is to be seen to be arrived at. Then what we have is those being the point in the space for the geometry. And then this increment, dispersion, and dimensionality is a lot like an account of the numbers too. It's geometry, but it's infinitesimals, iota values, making a 0, 1 unit line segment, a natural length unit line segment that is a continuum, a linear continuum. And then it makes all the rest of the geometry too, because then straight lines are just the shortest things that connect points in those. Those are all points, and so it's just like points and like real numbers, and then it establishes geometry's objects according to dimensionality, making the higher order figures, planes, volumes, and so on. So in that sense, it's very standard. You might say, well, what's standard? Yeah, it's like, well, standard usually means like you divide it by this fixed parameter, so then it's natural. So you like standardize and normalize the units of things. And then it's the same for like, well, what's the standard in the standard analysis? It's like, well, infinity is, it doesn't have much more to it. It's just all the finites. And so we say that we can relate that and we're fulfilling a supertask no matter what. It's like, well, what happens in infinity? It's like, well, there's no actual infinity in it. That was after that somewhere. So, and as you can see, then all these ideas that go in and they try and figure out was like, well, why do these three different cases for convergence and emergence by three different laws of large numbers, by three different interpretations of Cantor space and the back and forth and those, by by these three different limit laws in probability, all because there exists non-standard yet perfectly real infinities is kind of why it's so. So in reading in Foundations here is like, first of all, I studied that for 20 some years. Like, after, being a young man and being like, well, I better learn something thoroughly well. I was going to be like, well, it's going to be Foundations. That way there won't be much else to know. And so this is an account that includes both the formalism and all logical positivism. If you ever watch or read these posts, you know that there's a strong logicist positivism here and a strong mathematical platonism with it. That then these ideas about how to kind of rehabilitate some of these candidate for Foundations mathematical has a way to go about it, and there aren't any paradoxes in it. There aren't any contradictions in it, and it makes for some various accounts of why there are these three kinds of continuity, and it's hard to find those all put together in one place. I don't know any other one really, but I do know that mathematics has got like on one in the base of the foundation today they have standard real analysis, and then way up above somewhere they have like the line integral or Jordan measure. Except then it became renamed Jordan content because it was said, well, that's confusing people because those would be like these iota values, line rails, and we can immediately derive a contradiction from those living in the same world. It's like, well, it's still living in the same world. And then it's similar with this thing about the completely metrizing ultrafilter. So it's like variously it's a continuous domain to a continuous domain, when otherwise it's just kind of like, well, it's almost all, but it's not, all. With regards to limit theorems that arrive at these things justifying their existence, of course. But yet they're still aren't quite fully satisfying when there are some examples that are the other way. And so then how those could ever be part of the world together, this is kind of from the foundation itself. And finding it in the foundation, not so much adding anything at all. This is why eventually this axiomless natural deduction, axiomless geometry are required, because anything else is eventually just going to not be complete. So there's more replete is arrived at, and that is the way of things. It comes across that is as so simply as you just heard described, without much more than that, really. For your own reasoning, for your own interpretation, and to verify or not that for yourself, to pick that up or put that down for yourself, has that it's so that the theory this way has a way to begin to address natural infinities, laws plural of large numbers. So reading Derrida and Husserl is kind of when going to logicist positivism, they're like, well, now we have all science and we can pick up and put down any of these theories without having to think about it. Yet, what about geometry? Because we know that they're perfect circles. We know, or this is the idea that it's not just traditional, that geometry is somehow perfect. Mathematics, meaning mathematical platonism, platonism, it's never not been so. And then trying to frame that when nothing else is left behind, for logicist positivism, it's like, well, isn't that just like our empirical pragmatism ruling mathematics when it can never say what is a perfect circle either? So Derrida, and after Husserl is studying this, and it's because Husserl is saying, hey, this geometry has to be an infinitary thing. So it's just another example like Hilbert, like Leibniz, like Montaigne, Duns Scotus, Spinoza, Hegel, who have that there's a truly infinitely grand number. and it's as of the numbers. So the infinity is in, and that's not necessarily to be inferred from what these ones mentioned. We're just saying that there's an infinity at all. From before it's like, well, there are only infinitely many possible things. Well, that's the point, that there are those, and if there are those, then there may need be another, and so these natural infinities is how I'm calling them, and not so much because there's not really a use of that word already. We talk about the natural numbers and natural units, and it's kind of sometimes scalar infinities of cardinals or ordinals, or just a plain old infinity, the bookkeeping term for unboundedness with regards to the integral and the derivative, and the terms for the completions in the analysis, what converges, and so it's perfect in the same way. Then they say they're natural is like, well, they're natural and it's kind of organic, and so when cases of emergence come up for these halving and doubling spaces, it is like so. So that seems to be sort of a relevant appellation. So Husserli is trying to establish a defense of geometry as an example, as the best example of something that only exists in strong mathematical Platonism, yet that we have a theory of it, and then what to say of its objects, which are hardly defended as whether or not we pick up or put down a theory. It's always the same for somebody. It's abstract to the point that it's interobjective. Let's take a look and see what we might find from these books. So the electron theory of matter has this involved, of course, because particle physics is kind of a conceit to whether there's atoms or not, or Democritan as it's called here. It talks about the units of the potential electrostatic energy, about the radius, kinetic energy, the main features of the part of the energy of the field, the moving charge, which does not involve the acceleration. So in this book, it's talking about that there's three constants that they call C in this electron theory of matter. One is light speed, and the other is moving charge, and the other is a ratio of the electrostatic and the electromagnetic. So they're all kind of about the same at the limit in one case, like they all kind of converge to the same value, but then they roll up and down kind of differently. And so it goes to show that when in the rest of theory, then it's related to this, like, well, C is this infinity in terms of accelerating anything to it, because it would involve infinitely grand amount of energy to, according to mass energy equivalency, to accelerate something massy to or beyond the speed of light. And then with regards to the electrical charge, moving charge's velocity, it's a little bit different, and it's a little bit above. And then with regards to this electrostatic and electromagnetic ratio, it's a little bit different. It's usually less. And that along these ways goes to help to show that directly right in the theory of this surface of these kinds of ideas that aren't going to have another way to make them except kind of by these ways, about these natural units, they're natural infinities, and what that means when they're infinities. Because a natural unit would usually just mean something that's like, I've normalized and standardized the unit, it equals 1. And compared to like 99 or 3.5, it equals 1. Not infinity and not infinitesimals, see. So this helps to begin to introduce that's kind of the word that fits easiest and isn't overloaded already. Kind of like continuous topology and continuous domain. It's like, well, you're talking about a domain that's kind of has extent, density, and completeness and measure. And you're talking about a topology that is its own initial and final topology. Does that conflict with any others? No. Those are currently unoccupied, the terms continuous domain, continuous topology, and now natural infinity. but they're close. They're close to the existing terms, and that's where they go. So that's nice. So that just finding an example. Our results may readily be extended from a point charge to any finite geometrical distribution. These are definitely issues, and then as Richardson is in the era when there's being established how to build the models of analysis at all that have finite, fungible values in them at all. That's a regular course of discussion, whereas after that, it's like, well, that's all figured out. We don't talk about that so much anymore. We'll just say it results that is finite, and then that always goes without saying. And anything else is just kind of like, you got to make sure your boundary conditions don't allow there to be nonsensical solutions or these kinds of things. There is a great amount of the derivation that needs to be revisited to get it right, and especially when there's something that's like, well, there's at least 3 different non-standard kinds of standard infinity. They're all true in the ways that they are, and now that's for mathematics to figure out. That mathematics owes physics more and better mathematics of infinity. Newton's law, negative electron. Natural rotation of plane of polarization. Page 548. Let's see what it says about. There's no infinity. But on page 548, after talking about Zeeman lines, spectroscopy, so we got Zeeman and Balmer. Natural rotatory effects, Kerr's magneto-optical effect, reflected light becomes elliptically polarized when a magnet. To explain this effect, motion of the electrons in the metal. Naturally, the theory is more complicated than that of the inverse Zeeman effect. It is discussed at length by Voigt in Magneto and Electro-Optic. So, yeah, Faraday, Voigt, Larmor, Fitzgerald, and Heaviside have a lot going on that definitely is practical and anything applied, doesn't really fit in the theory quite directly. And so it's got its kind of own empirical theory. It's got its own units of things. With regards to then the standardized ones are kind of simplified and often work quite well for very, very many things. It talks about quartz and chirality, 3 dimensions, Pasteur, Van 't Hoff, and Lebel, about optical isomers. So this is about optics. And again, mentioning Drude, D-R-U-D-E, Drude. Very similar results. Talks about proportionality. The Curies, that I haven't read this yet very much before, and it talks about the minimum and maximum and averages and how those are used to their consideration of what are the measured and measurable terms that otherwise would be as of an infinite or beyond the finite, why the averages are added up. So there's more coming from the electron theory of matter, but that's just kind of what was to be found there for the moment. This Graustein's higher geometry has a lot of great ideas after like the how one might say space inversion, that we usually think in terms of delta epsilonics as like a point goes to 0 because it has somewhere to go, compared to like a point going to infinity because that's diverging to infinity. That does it get there? And then basically with regards to any other related rate, whether it gets there before or after at the same time. So the idea is everything kind of goes to 0, and then the space inversion is that as that point goes to 0, then over 1, its reciprocal and inverse goes to infinity. So they are the same, which is nice. Metric geometry, inversive geometry on the sphere, page 451. So, it's a couple hundreds of pages up in these books somewhere. Just kind of the definition of these terms. Yet at the same time, some of these would arrive at, like, what's the first, when a theory has as its first axiom the inverse, it would kind of be going along all the ways, whether it's like yes or not, yes or no, this is in this theory where this is an axiom. Because anything that fits all of the axioms of theory makes a model of a theory, according to model theory, is a model of the elements of the theory perfectly well, or not. And there are models of theories with broken models, that whether or not those hold these given things, that they do hold these given things, that is pretty remarkable. That our proof theory and model theory are considered equi-interpretable here. And then as with regards to something like these inversions. Oh, here's the inversion of regions of the circle on page 380 with regards to the axioms and so on, that's how they kind of come together. Inversive geometry on the sphere. In this paragraph, we propose to show first that the inversive geometry of the plane may be reproduced in all detail on the sphere, and I imagine in a couple different ways at least. Secondly, that the resulting inversive geometry on the sphere is identical with the projective geometry on the sphere. It will follow that the inversive geometry of the plane is abstractly identical with the projective geometry on any non-singular quadric, which has real trace but is without rulings. Well, that's interesting because the terms that would need to be understood here would be the trace and the rulings as with regard to the quadratic or quartic. A quadric, that being in the second order. And so that's with regards here to the parabola and the hyperbola, because the hyperbola is like x equals 1 over y, or y equals 1 over x, or xy equals 1. And then so that's like the hyperbola, and then the parabola is y equals x squared. And so x equals the root of y. And so then why that would be so, to relate in these things, and then with regards to the trace but not to rulings, it's kind of like the discussion when there's like the ordinals go out, and they have the increment, and whether they have dispersion and in their regularity make modularity is or isn't so. I mean, they might all just fill up between 0 and 1. They might all fill up between 0 and 2. Vis-a-vis filling up all the naturally many integers, all the infinitely many numbers, which the idea is that there is a model of those that they do, and so often that those are the same thing as a whole number, is that the ordinals are like given those as being the same, and they're a little bit less than that, and then the counts are given those as being the same, and that's a lot of bookkeeping to keep them all accurate. This is helping to show that this abstraction that's being defined as being like, and it's complete, and it's complete, and it's complete, with these reserves that are not so. Helps a lot reflect that this projective inversive geometry on the sphere is like the projective geometry with some caveats. So in the inversion of regions in the circle, a proper circle separates the points of the plane, except for those on it, into two sets of regions, the interior containing the center and the exterior. And that reminds of when reading Kazarinoff's theory of inequalities, and he was talking about Camille Jordan, and he was talking about how to define the interior and the exterior of a figure. And it's the exterior is infinite. And he says, which inverts into which? Suppose that C1 and C2 are two proper circles which are mutually inverse in a proper circle. The two regions bound by C1 must invert into the two regions bound by C2 for inversion as a continuous transformation. But which inverts into which? Surely the interior of C1 does not always invert into the interior of C2. So this helps to effect to reflect that these affectations of reflections, helping to show that grammatically and linguistically, I say that all the time, affect to reflect, and it means to affect to reflect. That these inversions result cases which are or aren't so. We leave the proof of theorem 2 to the reader with a warning. The point at infinity lies in neither half plane, but on the line. Or it makes a great circle around it. It makes it opens is another way to put that. Well, let's see here. That's about the reading for today. So it was a discussion of infinity in foundations, the object. So then the idea is that there's this natural infinity, and it's not necessarily all it's made up to be, and it's not necessarily not more than it's made up to be. That there are fragments and extensions. There's no standard model of infinity, yet there are these three natural infinities. Derrida says in Philosophy of Arithmetic, Husserl already distinguished between psychological temporality, a successiveness, and the temporality of the synthetic interconnection of sense. So these we just call kind of two continuities, and a kind of a subjective continuity and an objective continuity. That even in the disjoint there's the continuous. The origin of geometry, and then he kind of reflects on rejecting Galileo. It begins with the superficial commonplaces, the most obvious commonplaces. We understand our geometry, available to us through tradition. We have learned it, and so have our teachers. All right, then. Hey, have a great day. I hope you have a great day and that things are going well for you. Happy holidays this December 2024.